Hello anatomy students. Today we're going to talk about homeostatic regulation. Let's start off by answering the question, what is homeostasis? It is the existence of a stable internal environment. Now notice that I said the word stable and not constant. If you take a look at the picture that I have on this slide, you'll see that our body's temperature, represented by this red line, is not straight across directly on what is called the set point or the target. Normal body temperature, or the target temperature, is 98.6, but our temperature is going to fluctuate throughout the day. But as long as it stays within this normal range, then we're going to be fine. So it is homeostasis that is going to allow our body to maintain its values. And it could be body temperature, it could be the amount of sodium in our blood, it could be the pH of our blood, but it's going to keep our ranges or our values within a range that is acceptable. And by keeping these values within an acceptable range, harmful changes to the composition of our body fluids and our intracellular fluids will be avoided. So our cells and our tissues and our organs and our organ systems, they are going to perform something called autoregulation, which just means that they are going to adjust themselves in response to changes that they sense within our internal environment. A lot of the control over homeostatic regulation comes from our nervous system and our endocrine system, but more on that later. All right, so each homeostatic circuit is going to consist of three parts. We have the receptor, the control center, and the effector. The receptor is what senses a change in the environment, and it sends its information along to the control center. The control center is often the brain, but it could be another gland or an organ. And the control center is going to send a command to the effector. The effector is then going to create some kind of change. And that change is going to be usually opposite in the way that the stimulus occurred. So if the stimulus was an increase in temperature, then the effector is going to bring about changes in the body that are going to lower the temperature. So we call that negating the stimulus. The other 2 points that I wanted to mention here are the set point and the acceptable limit. So as I said on the slide before, the set point is like the target. So like our normal body temperature, 98.6, that would be perfect. But there are acceptable limits. You know, if I wake up and I take my temperature and it's 97.6, and then later on in the day it's 98.9, my body is not going to react adversely to that. The only time that one of these feedback loops is going to come into play is if our value goes outside of the normal range. We can use a thermostat to illustrate how a homeostatic feedback loop works. Homeostatic feedback loops are usually negative feedback loops. There are some rare examples of positive feedback loops that are homeostatic in nature. However, the majority of them are negative feedback. So let's take a look at my picture here with my thermostat. So when we begin, we are at homeostasis, which is normal room temperature. But then what happens is that as the sun comes up and it warms up the walls and the roof of the house, what happens? The room temperature goes up. That's your stimulus. We have now disturbed the normal condition of normal room temperature. This disturbance is sensed by the receptor, which is the thermometer, and that's usually housed within the control center in this case, which is actually the thermostat. So the receptor senses this change, it sends information to the control center, and the control center sends a command to the effector. The effector in this case is the air conditioner. The air conditioner switches on, and it cools down the room until normal condition is restored until we reach the normal room temperature, which is whatever you set it to be. You could set your thermostat to be 70 degrees or to be 68 degrees. And when that is reached again, then the effector or the air conditioner will turn off, and it will remain off until the condition is disturbed again. And it just continues going on in a loop. And so this is an example of a negative feedback loop, because our initial stimulus was an increase in room temperature, but when the air conditioner turned on, when the effector got going, it dropped the room temperature. Notice that these two arrows are opposite. That's why this is called a negative feedback loop. And once again, I just wanted to throw this term out at you. This is homeostasis is more like a dynamic equilibrium, which means that it's constantly changing. Like I said before, this red line that represents our temperature, it kind of weaves below and above the set point. It's not a straight line right along the set point. If it never changed, we would say that it was static. But the word dynamic means that it is constantly in a state of flux. But remember, as long as it stays within this normal range, we are good to go. So here's a negative feedback example that doesn't involve a machine. This is one that involves our body. And so let's say that we're in the house and it's a hot summer day, but we're in the house right now. Our body temperature is normal, but then we have to walk our dogs, right? So we go outside and the sun is blazing and it's 90 degrees outside. And what can happen is that our body temperature, if we stay outside for too long, it can start to rise. And we have now, I should probably not use a down arrow for that, silly Ms. McDonald. Our temperature has been disturbed. So now our temperature is going up. And this actually happened to me. I had to drive somewhere with my air conditioning off because it was broken, and when I got to my destination, I wasn't allowed admittance until they took my temperature, and the surface temperature on my skin was over 100.4 degrees, and so I wasn't allowed in the building. And so that's just an example of how this could happen. At least that's what I have going on in my mind right now as I'm explaining this to you. So our body temperature is going to go up. We have a disturbance here. And so basically what has to happen now is that a receptor in our skin is going to send the information to the control center. The control center in this case is the thermoregulatory center found in the hypothalamus of our brain. And when our hypothalamus senses, hey, our body temperature is starting to get a little bit too high here, it's going to send out signals to the effectors. And in this case, the effectors are the sweat glands and the blood vessels. The sweat glands are stimulated to release sweat onto the surface of our skin. When that happens, the sweat is going to evaporate into the air around us, and that's going to give us a cooling off effect. Also, I know that when I was going into this building, my skin, I was flushed. I looked red. I looked like I had a little bit of a sunburn there. And that's because my blood vessels were dilated and they move closer to the surface of the skin. The purpose of that is to allow the heat from the blood that's moving through them to dissipate from the blood through the skin and then out into the environment. So by releasing the heat from the core of my body, I was able to cool down a little bit. So the response then is that we have increased heat loss and the body temperature dropped. And that's exactly what happened to me. After I stayed outside in the shade for a while, I went back in after about 5 minutes or so. They took my temperature again and I was under 100.4 degrees. So I was able to go into the building then. And so once again, this is an example of negative feedback because the initial stimulus, an increase in body temperature, was negated by the response, which was a lower body temperature. In a disease state, the body is not able to fix itself like this. And so that's when you need to have maybe some outside help. Like maybe if I couldn't get my body temperature down, I would have to maybe go back home, take a cool shower, drink some cold water, do some extra things in order to try to lower my body temperature back into that normal range. Now, positive feedback loops in general are not homeostatic in nature. So say that with me. Positive feedback loops are not homeostatic in nature. And the reason why I say that is because even though like the example that I have on this slide is very helpful, right? Like the formation of a blood clot that's going to prevent us from bleeding out. But if this part here, if this positive feedback loop keeps going and going and going, we could continue to have blood clots forming all over our body. And depending on where they are, that could impair our breathing if it's happening in the lungs. It could cause a stroke if it's happening in our brain. It could cause a heart attack if it's happening in our heart. So, there is a little bit of caution here when you're looking at positive feedback loops. With a positive feedback loop, the effector is enhancing or augmenting the initial stimulus. So let's just take a look at what we have here in our picture. So we've got a cut in a blood vessel, and the tissue that is damaged is going to release chemicals, and these chemicals are going to summon platelets, which are really fragments of different cells, to come and block up the hole. It's also going to cause for a protein net to be formed to kind of try to draw the two pieces of the damaged tissue together. And as more and more platelets come in and they get stuck in this net, they are going to release more and more chemicals that call more and more platelets to the area. And they're going to release more and more chemicals that call more and more platelets to the area. And, while the blood clot that is forming locally here, and it stops the bleeding, and that's a good thing, right, about blood clotting, right? Like it's kind of helping our body to maintain homeostasis by helping our body to keep the volume of blood constant. But if these chemicals are flowing throughout our body, the danger is that they are causing blood clots all over the body. And so like that's what I was saying before, is that depending on where these blood clots are forming, it could be very detrimental to our body. And that's why we're kind of saying that this is not an entirely 100% homeostatic example for positive feedback. And so, if this was happening, and if the blood clot cascade continued and continued and continued, and somebody kept having blood clots popping up all over the place, well, then there would have to be some external processes that need to take place in order to restore homeostasis. Like, for instance, they would probably have to be hospitalized and given a blood thinner like heparin or Coumadin in order to dissolve those excess blood clots that were occurring throughout the body in order to help restore homeostasis. And just, I wanted to make a quick mention that another really common example of a positive feedback loop is the birth of a baby. I'm not going to talk about it here because you're going to look at it on in your activities in class. The thing to remember, though, is that all of our body systems are connected. Remember, homeostasis is a dynamic equilibrium. So each system is going to work in its own way to maintain a normal range of values. But if one system, and let's just say that it's the respiratory system, so if one system starts to kind of break down, then the others are going to do things to augment and kind of help that broken system along. again, with the goal of ensuring that we survive.